Welcome, everyone. I'd like to introduce Michael Sutherland. He's an oceanographer, been working in the energy industry for about 10 years. And he's here to talk about climate change and some solutions. Welcome.
Thank you. Well, I'd like to thank Dina for inviting me and the Charlotte Hobbs Library for hosting this talk, and for everyone here and virtually who has come to attend. So I'll begin the PowerPoint now, and I've added one section from the title. It said past and future, and as I put the talk together, it became pretty obvious I'd want a third section, present, obviously dealing with a snapshot of climate conditions as they are today. So I'll be going through my set of slides, introducing you to the basic science behind global warming and the history of the theory. So some of the people who've put together the ideas as we now know them, give you a brief snapshot of the state of the science as it is currently, and then some of the prospective realities we face if we either don't mitigate or some of the strategies that we can employ to to reduce the global warming effects. So I'm going to begin the PowerPoint presentation now, and I hope you enjoy it. And let's see which screen comes up here. And let's give this just a moment. Okay, so hopefully, yeah, you all have that full screen view of the title slide. So really, climate change, past, present, and future. I could sort of, shoehorn that in, but so let's begin moving on. Oh, it's transcribing everything as I talk. I was getting distracted here. It's recording my words as I say them. So anyhow, so the first part of this talk, we'll be talking about, or I will be speaking about basic science, results of past research, how we assembled our current understanding of global warming, essentially, and how we came to our present, the present state of our theories on the subject. So first, I thought it's worthwhile to begin with really the basics. That is, what is weather? And simply put, it's the measurable state of the atmosphere. So temperature, humidity, pressure, all the things that we can use instruments or satellites for, that constitutes what we call weather. And really what the weather is the result of is the distribution of solar energy from the equator to the poles, because the vast majority of the sun's energy strikes the tropics, being the most directly facing the sun, and that energy wants to distribute more evenly. So we wind up with the fluid dynamics we call weather, with storms and wind and all those things that we're familiar with. So moving on from weather, then what is climate? And it might seem absurdly simple to say that climate is simply the long-term average of the weather. So, temperature, humidity, all those same things, the long-term conditions under which a region exists are known as climate. Now, what constitutes long-term is where people can differ, and if you're doing a research paper, you just want to make sure to precisely define your terms. Is it 100 years, 1,000 years, 10,000 years? Just what's the time scale you're operating on? And when it comes to global warming, we find ourselves operating sometimes in timescales as small as a decade, which becomes difficult because there's a lot of noise in the weather signal. So things can fluctuate quite a bit from year to year, but up to scales of 1,000 years, certainly we'll compare the present day to previous to the industrial era. So the climate being basically the long-term average of the measurables that we know every single day. Now, climate change basically then constitutes the change in those long-term weather patterns. And these can come in the form of global changes or regional changes. And one example of a regional change would have occurred during the last, after the last glaciation, when the early version of the Gulf Stream used to come up the east coast of Florida, and then from Cape Hatteras in what we now know as North Carolina, headed more or less due east towards Spain, so that all the warm water would head straight east, and that area of the world would have been probably warmer than it is now. But following the glaciation, when the removal of the ice allowed the current to then take a much more northward trajectory. And so this is what we know now, where the Gulf Stream becomes the North Atlantic current and eventually terminates east of Iceland, where a lot of the water evaporates. And that evaporated water is what gives Northern Europe basically the ability to be inhabited. Otherwise, it would be much too cold. So the Gulf Stream really makes Northern Europe and Scandinavia livable. And a change like that certainly affects one part of the world dramatically, but it doesn't change the overall energy state of the entire planet. It's simply shifting heat from one area of the world to another. And the ocean is a tremendous driver of climate. Water is roughly 1,000 times as capable of carrying heat as air is. So changes in ocean currents will have tremendous effects on the overlying atmosphere. So that would constitute a regional change. But global change, we're talking more about changes in the overall heat content of the entire planet. And so this is a larger scale. And the number one variable for that is how much energy is the sun outputting, which is largely constant, but not entirely. And over the course of the sun's lifetime has changed quite a bit. The arrangement of continents actually, that affects how the ocean currents and how the air currents move, how efficiently they can move heat around, and land tends to hold heat less efficiently. So depending on where that land is located, it can lead to a colder or a warmer Earth. And those dynamics are still very much under study. You know, as geologists look at the past arrangements of continents and we try to model what the climate might have been at those times. And then, of course, the one that we're so familiar with these days is the greenhouse gas concentration. And so we'll be going into a definition of what the greenhouse gases are shortly. But variations in that content will have a huge effect on how much heat can even be stored in the atmosphere. So to start with number one, solar output, the sun is a little over 4.5 billion years old. And due to our, based on our astrophysical understanding of other stars and our modeling of them, the sun has gained about 30% brightness over the last 4.5 billion years. It's about a middle-aged star, so it's going to live for another 3.5 to 4 billion years. Right now, it's burning hydrogen about as quickly as it ever will. So it's at or close to its maximum brightness as we speak. Or you might say the sun is maybe just at or a little over the hill in terms of its lifetime. So this is about as bright as we ever expect it to be. And so this chart here, it's a very crude chart showing projected early output of the sun. And as you can see, geological records show that there was actually much more carbon dioxide in the atmosphere earlier. But because the sun's output was less, the climate was actually colder at that point because there was less heat coming in from the sun to trap. So carbon dioxide, as we study the Earth's ancient past, we realized that greenhouse gases are a significant impact on climate, but not the only, far from the only. And the fact that right now carbon dioxide is one of the controlling factors is simply due to a number of other things behind the scenes. So solar output, as far as we're concerned within historical times, is essentially constant. And it does vary a little bit. We have a sunspot cycle, which goes up and down about every 11 years, and that's measurable. So the sun's output will fluctuate, but that's not a trend. It's a mean around one single value. So that really is not something important for the global warming theory. So this graph, we could easily spend a half an hour on this, and I'm not going to, but the solar constant is essentially what we've measured in satellites to be the steady input from the sun in terms of all available heat energy, generally ultraviolet radiation. And so at the very top of the atmosphere, so before it's blocked by any gases, generally speaking, we're receiving 341.3 watts per square meter of solar energy. And a couple of points that I want to make based on this graph. If you look on the left side, or maybe let's see, as you're looking, it's going to be, yes, on the left, the input of 341, and that is balanced by the energy reflected from the atmosphere, 102, plus the energy that's radiated out from the Earth, 239. So inputs equal outputs in terms of thermal energy. So that means the planet would be in stasis, that the same heat energy that comes in, it expels just as much. So the planet's in thermal equilibrium. And the other point I'd like to make is that if you look in the lower right, you see where the Earth re-radiates quite a bit more energy, 356 watts per square meter. But then most of that is reflected back down or radiated back down due to the greenhouse gases. So this is a cycle that we're really going to be focusing on for the purposes of this talk. But there's one issue with this graph, and that is right now, the inputs do not equal the outputs. In fact, the outputs are less than the inputs. In other words, the planet is currently gaining heat energy from the sun. About 1 watt per square meter less is being re-radiated back out into space as opposed to what we're receiving. That stored heat energy is what's leading to the added temperature in the ocean and the atmosphere. And we've been measuring this, ever since the advent of some of our climate and weather satellites. We've been able to estimate the reflected energy or the radiated energy. And from 2000 to about 2018, it's nearly doubled how much energy is being stored within the planet versus being radiated back out. It might seem like a very small amount, less than 1 watt per square meter against 341, but variations like that, small variations over a long period of time will have a tremendous effect on the state of the climate. So what we're looking at right now is a thermal imbalance, as due to the added carbon dioxide, the planet is warming up. So it's going to be reaching a higher energy level before it stabilizes. On here. So to go into the actual greenhouse effect, I'd like to bring in a few factoids of history. The person who is credited with discovering this effect was a Brit named John Tyndall, and his experiment was to emit infrared radiation into a closed container. And what he did was he would alternately fill that container with different types of gas, and then he would, over time, measure the temperature and see how long that heat was retained. And he found easily the best heat retention was by these so-called greenhouse gases, carbon dioxide, water vapor. And so he was the first one to really identify this as an actual chemical reality. So to extrapolate this to the entire planet in terms of the importance of greenhouse gases, if there were none, the Earth would be considerably colder than it is now. It'd be well below freezing, 0 degrees Fahrenheit. So it wouldn't be survivable for most life, or for certainly most large forms of life like us. We'd find it very difficult. And with the greenhouse gases, as of year 2020, excuse me, according to NOAA, the global average temperature was 47 degrees Fahrenheit. So nearly 50 degrees due to the presence simply of carbon dioxide and other insulating gases in the atmosphere. So they are tremendously important for life as we know it. They are not threats to existence by themselves. Changes in that will have large effects in climate. And so that's what we're discussing today. Carbon dioxide itself, on a molecular level, is one central carbon atom with 2 oxygens on either side. And it is the principal product, along with heat, of combustion: wood, oil, coal, gas. That's the main byproduct. Now, carbon dioxide has the chemical property where it will absorb infrared energy and store that energy in the chemical bonds. So the oxygen atoms start vibrating against the carbon, and that's where the energy is stored. The molecule doesn't particularly like being in an agitated state like that, so it will soon re-radiate that heat energy back out. And because carbon dioxide can absorb the heat, it wants to expel the heat rather than break down. So when we bring this out to the global, extrapolate to the global level, the sun is emitting ultraviolet light, which the Earth absorbs. And then much of that is re-radiated out as infrared energy. And that energy is then absorbed, much of it's reabsorbed by the carbon dioxide. And the carbon dioxide then emits it in all directions. So that heat energy, which is emitted back down, is then the insulating effect. Some of it's emitted up, so that will be lost to space, but much of it's sent back down to Earth. So the more carbon dioxide, the better the insulating effect, and the more heat overall is retained in the system. So the result of increasing carbon dioxide content, obviously atmospheric temperatures will increase, that will change weather patterns. The oceans will warm, we'll be looking at some of the effects of those. The ground heats up, and that's had effects on plant species and insect species that live in the soil, which have, in some cases, a very narrow temperature range. And so they can't survive warmer soil very well. And then ice loss, which is one of the larger problems facing us in terms of sea level, is ice caps in Antarctica and Greenland, which are destabilizing because of growing temperatures. And that is one of the larger sources of anxiety, because if a large ice sheet let goes quickly, we're looking at a catastrophic increase in ocean level on the order of decimeters to even a meter. So that's one of the larger concerns we face. Now, the greenhouse gases themselves, obviously carbon dioxide, water vapor, methane is one I haven't talked about. It's a naturally occurring compound. And methane is a much more efficient greenhouse gas than carbon dioxide. It can store far more energy. However, methane does not reside in the atmosphere for nearly as long. It will stay there for on the order of about 100 years before it descends back down to the ground. Carbon dioxide can stay in the atmosphere for well over 1,000 years. So gram for gram, you might say, the carbon dioxide will ultimately have a larger heat releasing effect on the atmosphere than the methane. But over the short term, the methane has a far larger impact. A number of industrial era compounds that will be released through either combustion or other processes, nitrous oxide, ozone, which is a problem where automobiles are common, which is most of the planet. Chlorofluorocarbons, if you remember all the issues with refrigerants and the destruction of ozone back in the 80s, and we've since outlawed those, but they still do exist. Perfluorocarbons, which are used extensively in the medical industry. And then sulfur hexafluoride, which is probably the strongest greenhouse gas of them all, but it's present in only trace amounts in the atmosphere. So it doesn't really add meaningfully to the discussion. Overwhelmingly, carbon dioxide is still the concern here, seconded only by methane. So I would like to switch gears a little bit here. Moving on from the chemistry, we're now going to look at something more macroscopic. We're going to be looking at variations in the Earth's orbit and its rotation, because these have profound impacts on the climate, especially the chart you're looking at right now called eccentricity. And the Earth does not orbit the sun in a circle, it's an ellipse. And that ellipse does not always maintain the same shape. The eccentricity of an ellipse is a measure of how thin and stretched it is. More eccentric, it's thinner and it's more stretched, and less eccentric, it's closer to a circle. And this is extremely exaggerated. The eccentricity of the Earth's orbit, I can't quote the number, but it's well less than 1. It's a very small number. If you were to look at it, it would look circular. But differences between the more eccentric and the less eccentric orbits do have an impact on how much solar energy reaches the planet throughout the year. And at this point in time, the Earth's orbit is in a more eccentric stage, but it's tending back toward a circular form. So we're becoming a more or a less eccentric orbit, I should say. And the other cycle to bear in mind right now, and this was discovered by a man named MILANKOVITCH, and he did his math at a cafe in Serbia in the early part of the 20th century as he was working out these theories. And this would be variations in the Earth's tilt, which right now, it's about 23.5, 23.44 degrees. And it's actually moving toward a more vertical angle with respect to the ecliptic, which is the Earth's orbital path around the sun. So the Earth basically wobbles, and that wobble changes a little bit over the course of about 40,000 years. So what amounts to this is we have beats in the Earth's orbit and its rotation. And these beats, these rhythms of change are what lead to now the cycles of glaciation that we've had for the past several million years. And I'm not aware if the physics have precisely been worked out, but if you look at the middle band here for the eccentricity, and then correlate that to the stages of glaciation, where the peaks are the interglacials. So where it's been warm, like it has been here on Earth for the past 10,000 years, and then a quick descent into the coldest temperatures. So the glacial phases will be where the graph, are showing the minimums. And those minimums correspond pretty closely to the least eccentric orbits. So the more circular orbit, oddly enough, corresponds to the glaciations. The more elliptical orbit corresponds to the warmer phases. And why exactly this is the case now is a subject of active research. Why it is that the Earth's climate is now in such a tipping point, or such a balancing point, that it fluctuates so greatly over over such small variations in the orbit. It has not always been that way. At some points, the climate was far warmer than this. It was what we call greenhouse, where there was no ice. There was no permanent ice cap. So continuing to look at the last 500,000 years or so, these are two temperature records that we've been able to reconstruct from ice cores in Antarctica. And then down here, they flip the graph just to make them look the same, but it sort of makes the interpretation a little more difficult in my mind. The higher temperatures correspond to low ice volume, and then the low temperatures correspond to higher ice volume, even though that axis is flipped down there. And that stands to reason. So this then, we can correlate the temperatures almost perfectly to carbon dioxide content over the past nearly 1 million years. The two graphs follow each other very, very closely. So carbon dioxide being so perfectly correlated with global temperatures, it has been basically the dominant, element for temperature changes globally over the past, 2 to 3 million years, I would say, while we've been in this glacial and interglacial phase. And we're going to look a little bit right now at much farther in the distant past. So this is several billion years ago, but temperature reconstructions through gases trapped in rocks and things like that, we've been able to put together a very rough reconstruction of the overall Earth climate temperature throughout geologic history. And the one thing I want to draw attention to right now is the middle part of the graph. From about 300 million years ago to 200 million years ago, we were in what was called a greenhouse phase. So there were no polar ice caps. Basically, the entire ocean was open. Versus now, over the last, certainly within the last couple of million years, very tail end of the graph, we're actually in what's called an icehouse condition, where there are permanent ice caps on the poles. So the Earth as we know it, that we've evolved in, is actually one of the colder climate states that the Earth has known in its existence. And the reason why I want to draw attention to those two different areas, the greenhouse phase corresponds to the existence of the continent Pangaea, when all land was gathered together into one huge mass on one side of the planet. And with all the land together, for reasons that we're still trying to understand, this led to a much hotter overall climate. And the climate as we know it now, of course, being colder, the Earth is, as we see, the continents are far more spread out. So impacting ocean currents, the ability of the ocean to transmit heat around and efficiently store it. These are the background to why carbon dioxide is now such a prominent factor in deciding or basically determining the fluctuations between an ice age and an interglacial like we're in right now. So another note on sea level, which we'll be returning to a little bit later. I just wanted to define the term. There are two types of sea level that we measure. One is EUSTATIC, and that is geometrically from the center of the Earth outward. That's what we measure using satellites. And satellites are a tremendously important part of our climate monitoring system. And NASA actually is the caretaker for most of the climate data that we have because they run satellites. So you would think of NASA as, trips to the moon or Mars, things like that, which I will say are worthwhile, but they're the ones who really administer most of the data we've been able to learn about our weather systems and our climate history outside of geological records. And for fluctuations in global sea level, basically, whether it's a greenhouse or an ice house, in greenhouse conditions, all the water's in the ocean. In ice house conditions like now, most of it's locked up on land. If that ice were to melt, then the oceans would rise considerably. And another, which isn't really part of our part of the talk tonight, but the ocean ridges in the middle of the ocean, which cause the ocean floor to spread, at times those are much more active. So the volcanic activity within the Earth goes through periods of real, of a hot phase where there's basically excessive volcanic activity. Those ridges will get bigger, and they can actually cause the ocean to rise by as much as 300 meters. So when we look at gigantic ocean level changes across geologic history, most of those correlate to geologic activity and not, not the temperature of the planet. But that again, it's just another example of where the climate system and the ocean system are very complicated with many inputs. So even though carbon dioxide now has an outsized impact on our weather and our climate, it was not always so. There are times when other influences are far stronger. And the other type of sea level we mentioned, or we study, is relative. So these would be things like tidal gauges, or if you've got any kind of benchmark along a coastline, and you're looking at changes over decades or centuries, relative to that baseline, what is the sea level now? And if you've ever been, along the Maine coast, if you ride onto Portland and you see the mud flats down there, that was once ocean floor, probably about 100 meters below the surface. So that mud was laid down beneath the ocean. But what happens is after the glaciers melted away, it's like a person stepping out of a rowboat. The impact of the glaciers on the continental crust depressed them by several hundred meters. Once the glaciers were gone, the crust rebounds, it rises up. And so the mud flats that we see now in the tidal plains around Portland were once sea floor, but when the glaciers melted away, this part of the crust rose up several hundred feet, and now that ancient sea floor is now a tidal mud flat. So we see examples of this around the world. Canada and Scandinavia still feature areas where the crust is rebounding quite rapidly, so that there is measurable uplift every single year because the ice was only comparatively recently removed there, and rock, being rock, moves slowly. So the rebound by our terms happens extremely slowly, but it's still going on. So now we'll address some of the history of global warming theory itself. And it's generally acknowledged it begins with a man named Svante Arrhenius. And in the late 1900s, he took interest in this greenhouse gas that had been identified earlier that century. And he began modeling what would the impact of increasing or decreasing its presence in the atmosphere. And he found that if you went from, at that point, with the current concentration, about 250 parts per million, down to 125, then it would plunge us into another ice age. And in fact, records that we have indicate that it would be a very severe ice age that would result. And then on the flip side, if you were to double it to 500 parts per million, you'd wind up with a catastrophic increase in temperature. So he was the first person to really make this theory explicit And unfortunately, like a number of other scientists at the time, his ideas were largely ignored for about a half a century. So really, there was no further discussion on this until the 1950s. And following World War II, there was a huge burst in oceanographic activity. And throughout the 50s and early 60s, there were seemingly big new discoveries every year, where we had really a fleet of research ships out there and gathering enough data to begin assembling a better picture of what the state of the ocean is. And they began measuring the chemistry of the ocean as well, and comparing that to models of how much carbon dioxide had been emitted into the atmosphere. And they saw the two did not equate, that not as much carbon dioxide was in the ocean as had been produced by combustion. And that led them to start concluding, researchers to start concluding, that there was a growing excess of carbon dioxide, which might well be leading to increased world temperatures. So this was now back on the radar screen for scientists. And in the 60s, work slowly continued. And now with the aid of modern computers, they were able to take some of the data from all the ocean sciences that have been gathered and basically revisit Arrhenius's work from 60 years earlier and come to largely the same conclusions, that removing carbon dioxide would lead to a plunge in world temperatures, increasing it would increase them greatly. And in 1969, NATO went so far as to form a committee of scientists to begin looking at this officially. In 1972, a researcher by the name of John Sawyer published a paper making this very clear, that carbon dioxide was a potential hazard for society as we know it, and that it had been conclusively demonstrated at this point that that the increase in carbon dioxide levels due to combustion were starting to have a noticeable effect on our climate. And I think he was the one who might have coined the term greenhouse effect. You know, he had it in quotes, but I think he's really the one who popularized it. And in the late 70s, well, in the mid 70s, there was a bit of a controversy because a number of researchers found that the ice caps were actually increasing in size. And that led people to wonder, well, is the Earth getting colder? It's about time we head into another glacial age. It's been about 10,000 years. And according to previous glacial cycles, that's about time temperatures began dipping again. And the increase in ice cover led a number of workers to think that, yes, we are actually on the verge of another ice age. But enough data was gathered from elsewhere on the planet that it was determined that no, actually, that's a local effect, that the world was in fact still warming up. And in 1979, the World Meteorological Organization organized a conference around this explicit idea that the world is in fact warming up due to our agency, and that there would be observable effects by the year 2000, and there would be significant effects for society by 2050. And I would say that prediction has proven so far to be pretty much right on. And we've already seen several significant effects. So moving into the 80s, one of them, you might say, the rock stars of the climate movement is Dr. James Hansen. And there are a few people who really have had more of an impact than he in terms of furthering our understanding and also making that understanding publicly aware, publicly available. And so he gave testimony before Congress and really sounded the alarm, sounded the official alarm that there's a problem we now have to fix. And that's when the United Nations formed the Intergovernmental Panel on Climate Change, which became basically the world's official gathering point for data on the climate and for research on climate change. So their voice really is authoritative on the topic. And just a quote from their charter on the IPCC was created to provide policymakers with regular scientific assessments on climate change, its implications and potential future risks, as well as to put forward adaptation and mitigation options. Essentially, the IPCC is an arm of the UN to provide national leaders with useful, accurate information in order to form policy. That's really all they're there for, is to assist governments in managing this crisis. And in fulfilling their mission, they've produced dozens of reports, but they have roughly cyclical assessments that they will release. The first came in 2 parts in the early 90s, and then the last was in 2014, the fifth assessment report, and the 6th is due out next year. Actually, next month in July is when, they'll be releasing the first part of that, what's called the physical science basis, where they lay out essentially all the different evidence streams behind our awareness of global warming. So temperature records from around the world, satellite data, ice cores, everything that we have to contribute to what we know. They release that first report in about 3 weeks from now. So I'll be downloading that as soon as they do. But it became clear at that point that official action was now necessary. So in 1992, the Kyoto Protocol was adopted, and it came into force in the early 2000s. And these were unfortunately unenforceable goals of reducing carbon emissions. And the goals were written very loosely based on the size and the economic advancement of countries, where countries that are less well developed would be allowed more of a carbon budget because they didn't have access to higher technology. And basically, despite the good intentions, the Kyoto Protocol was more or less a complete failure, and it really didn't slow down carbon consumption at all. And during the time that it was supposedly in force, emissions increased by 1/3. So it really did not fulfill its aim at all. So that brings us to the 2015 Paris Agreement, which again isn't enforceable, but the goals at least are stricter. It still does allow each country separately to maintain their own goals. And that's really been one of the major obstacles to concerted climate action around the world, is no country wants to give up its sovereignty on this or any other topic. So they're not going to be told what to do by the UN. And that makes action really, unenforceable. And in some cases, if one country bucks the trend, you'll wind up with a whole bunch of countries following that bad lead. And we unfortunately were the worst among those over the last few years. Biden is trying to re-enter the agreement now, and hopefully, drag some of the other unwillings along, like China, because China and the United States are the 2 largest emitters of carbon dioxide. So really, as we go, the world goes. That's basic. That's the basic reality of it. So it's up to us to show leadership on this subject. And this concludes the past portion. So now I'm going to go into the present state of the climate and what we're witnessing now. And that would be, over the last 60 years, carbon dioxide concentration has increased to over 400 parts per million, which at one point, the 400 mark was sort of a red line in terms of just being an unacceptably high number, and now we're above it. And it correlates closely to rising air, ocean temperature, the loss of ice. So basically the predictions of what would happen with this level of carbon have so far come true. The models, if anything, have under-predicted what would happen in terms of temperature rise and ice loss. And with this increase in temperature globally, since 1960 or so, about a 1 degree Celsius increase. For one thing, it's important to bear in mind that this isn't just an even 1 degree linear step all over the world. The changes are uneven. So some parts will get much warmer, some parts not quite as much. The climate system is extremely complicated. So you can't simply take a stepwise increase. It's going to have effects all over the place on different timescales. So, for example, the United States is predicted overall to get warmer. The Southwest is predicted to get far warmer than anywhere else. The Northeast, where we are, is predicted to get much wetter, but not in the nice, pleasant, drizzly rain that might be good for farming, but it's modeled that we're going to get more prone to torrential rains, which are actually harmful to plant life. So yes, we're not going to be suffering from droughts, but it might not necessarily still be beneficial for us. Whereas the Southwest in 50 years, if this continues, could well become close to uninhabitable. It's already, they have heat waves of 110 degrees, 120 degrees out there, and they are running out of water. So if that's exacerbated, then part of this country might well become like the empty quarter of Saudi Arabia. So a lot of these temperature and weather effects are really regional, even though the problem is global. And there's another concept over the last, I would say 10 or 15 years, that's become a pretty popular one to talk about, which is global weirding. And that would be the disruption of the weather patterns that we're used to, normally or mostly in the form of increasingly extreme events, either increasing in frequency or increasing in severity. And so I'll look through a few examples of those. And then in terms of the oceans, we've measured by satellite that they are increasing by about a little over 3 millimeters a year. So over the last 25 years, that's about 10 centimeters of increase. And if that stays the same, then that will put a lot of our coastal cities in danger, because not that New York would be underwater, but flooding events would become that much more common. So that infrastructure like subways and ports would become much more difficult to maintain or even use. So we're looking at the very least at coastal cities and installations being more difficult, to maintain in their current form, if not outright impossible to use, depending on local sea rise. And acidification is the result of when carbon dioxide is absorbed by the ocean. The ocean does take some of it up. Unfortunately, the CO2 dissociates into a weak acid, so that the ocean has become slightly acidic over the past 100 years. And this has had devastating effects for things like coral reefs and a number of other organisms which build shells. The acid dissolves those shells. It kills coral. So we are looking at a mass die-off of coral globally. So the ecosystem of the ocean is being profoundly affected by not only the temperature, but by the chemistry due to this change. So to look at a couple of plots here, this is a historical plot of carbon dioxide, and we're looking at the glacial. So the high points are the interglacial, and the low points of low carbon dioxide are the glacial phases. And the one thing I want to draw your attention to is never is the carbon dioxide higher than 300 points per million until the present day, when you've got the spike at the end, and we are a shade over 400. So this is out of all historical norm. We are bucking any historical trend. We've, by over 100 parts per million, we're beyond any natural carbon dioxide cycle as a result of our industrial activity. Now, this graph is the backbone of global warming science in terms of the evidence that this change is really occurring. So Mauna Loa, Hawaii, on top of the mountain, is the go-to observatory for carbon dioxide because it's the farthest away from any other land-based interference like cities. It's not downwind from any other major industrial centers. So it's looked at as the best location available to monitor the carbon dioxide content of a mixed atmosphere without local effects. And the increase has been dramatic from 1960 up to the present day. And what you see, the red there, the spike, that's the summer to winter fluctuation. So that in the summertime, when the trees, when photosynthesis is occurring, there's a drawdown of carbon dioxide. So that will be the trough is in the northern hemisphere summertime, and then it spikes in the wintertime when there are fewer trees. There's less photosynthesis going on. But that record is basically positive proof of our impact on the environment. And a temperature record, this is a newer version of the infamous hockey stick graph, where you have fluctuations in temperature over the last few thousand years. But once again, like carbon dioxide, you have this massive increase at the very end. And that's what we're looking at right now, is the result of our industrial activity, is bucking all natural cycles. And over the last couple of decades, a little more slowly, you see the same temperature rise from about the 1950s or so, 1 full degree temperature gain, modeled to be a few more degrees by the end of the century if we don't change anything. And sea level, this is from the last glacial phase when the ocean was about 120 meters lower than it is now. As the glaciers melted, that water then flowed back into the ocean. So it came up to the level we know now, but over the last 25 years or so, we've gained 10 centimeters due to ice melt. 2 effects, ice melts, and then as the ocean warms, the water expands. So thermal expansion plus ice melt are why we are gaining volume in the ocean. And then the ocean itself is getting warmer. The ocean surface, the temperature there has been noticeably warming. And in the last 15 years or so, we've been sending instruments to monitor temperatures at greater depths, so 1,000 meters, 2,000 meters. Those are warming as well. The entire ocean, top to bottom, is getting warmer. So we can't count on that to basically be the repository for temperature, and we don't notice because it can't store everything. The ocean's not able to hold all the heat. And the last graph here, sea ice loss. And again, our models are somewhat underestimating the actual volume of ice loss in the Arctic. And the problem with Arctic ice loss, the ice is sitting on the ocean. So if that melts, it's not going to increase the ocean volume. But what it does do is the ice reflects a lot of heat energy. That's called albedo. So when the ice is gone, the reflectivity is much less. So then the open water is absorbing most of the heat as opposed to reflecting it. So that's a feedback. That's one of the worst feedback cycles that we're engaging through the loss of sea ice. Global weirding, I mentioned, you're changing weather patterns, and there are literally hundreds of examples of these over the past couple of decades. A few of the better known ones would be the floods in Houston, Texas. They've had a couple of hurricanes down there, which basically sat over the city for a couple of days. And they had, I think, 2 500-year flooding events within about a year or two of each other. And the wildfires, especially last year in Australia, where Sydney was under threat for a while, the flooding in Pakistan, which I think flooded close to half the country about a decade ago, and then Superstorm Sandy, which devastated New Jersey and New York, and that under ordinary circumstances would have been a tropical storm or tropical depression, and it would have been trouble, but it wouldn't have destroyed the area. However, since the ocean was abnormally warm there, the storm gained strength as it came north, and it became even more destructive. But the main example I want to talk about right now is the polar vortex, or the extreme cold events we've had in Texas and Louisiana over the past few years, which people will say, well, it's ice in Texas, there's no global warming. Unfortunately, it's not that simple. What we have is the jet stream, a very strong current of wind, which goes west to east around the planet, and it separates temperature zones from one to the other. So north would be colder air and south is warmer. And when the climate system is as we've known it, the jet stream is very coherent, it's very strong, and it maintains that boundary very strongly. However, when the pole is warming up, as it has been, the temperature difference is less pronounced from north to south, the jet stream weakens and it starts to fluctuate quite a bit. And that's when we begin to see these huge dips to the south. So a healthy jet stream looks more or less like this, where there will be some waviness, but the jet stream we've been encountering over the past several years have been huge north to south fluctuations, where the entire continental United States might be covered by Arctic air. So that Louisiana and Texas will have freezing temperatures like they did last January or last February, and with catastrophic effects for Texas, where their power grid went down for a week. So that actually, the cold in Texas is a function of global warming, reducing the strength of the jet stream. So now moving on to the final section, the future, what's next? And if we were to basically continue as we are, the business as usual scenario, which is kind of the worst case scenario, we'd be looking at a global increase of up to 6 degrees, which would, in a lot of ways, end society as we know it. Especially, the impacts along the coast would be devastating with a rise in sea level. And even on dry land, the increases in temperature would affect things like species patterns, where the species that are mobile, who could migrate to a more temperate zone, their food supplies can't necessarily migrate with them. And the effects of where we can, where our agriculture will function, it will affect our economy. So we're looking at the business as usual scenario really being, I would say, something close to guaranteed destruction. And a number of countries like the Maldives, which I think they average about 1.5 meters above sea level, that entire nation will be underwater in 50 years if we don't do anything. Bangladesh would lose much of their territory. Florida, a good portion of Florida would be underwater. So business as usual is really not an option as regards this problem. And the weather patterns would, of course, change quite a bit. And there's a lot of modeling going on. I described how this part of the world will become more subtropical than anything, with increased sustained rains, not uninhabitable, but the species that we know here, most of them would not be able to survive in those conditions. So it would change the ecosystem here dramatically. And I think I've already discussed the impact on the farming industry. So the absolute worst case scenario, if we went into a true greenhouse condition where there were no ice caps, the sea level would go up by about 60 meters. And so none of our coastal cities would remain. And this would be, within 100 or 200 years. So that's kind of the doomsday scenario that you don't really want to throw out because you sound like a Chicken Little. But scientifically speaking, that is the end possibility. So that's certainly one thing that we need to keep in mind. And in terms of temperature impacts, it's odd that most of the increased temperature will be closer to the poles. So that's where, unfortunately, where a lot of the ice is released. So where we can least afford the temperature rise is where that seems to be happening most quickly of all. So what can we actually do about this? And the obvious answer is move away from fossil fuels as quickly as possible. And that's not an easy proposition because our economy right now is still based on oil. So that's going to be a decades-long prospect. But one way or the other, we will, whether it's by volition or not. And it was quite interesting. Only a couple of weeks ago, the International Energy Agency, which is not, it's another, it's not a function of the UN, but basically the world's most advanced economies set up the IEA a few decades ago to provide, just like the IPCC, to provide reliable information to world leaders on energy. It was basically in response to the oil shortages of the 70s. So how to cope with energy shortages. And their most recent pronouncement is that we shouldn't spend another dollar on increased extraction, that what we're able to extract right now with the infrastructure in place is what we should go with. And all of our investment now should go into renewables. Now, unfortunately, that's not likely to happen, but that the IEA is saying this is pretty telling because they have been one of the biggest cheerleaders for petroleum over the past 3 or 4 decades on Earth. So they've entirely changed their tune. And that should be a wake-up call to anyone who's listening. Carbon capture is often discussed, and I put that in the class of clean coal. Clean coal doesn't exist, but carbon capture is of such limited use and it's so expensive. That's not a realistic mitigation option. Really, what we're looking at is changing our energy sources, and that's going to have to primarily come from renewables. And scaling those renewables up is the huge problem facing us for a number of reasons. The first of which being they're unreliable. They fluctuate. The sun rises and goes down. You get weather. There's cloud cover. The wind isn't always blowing. So these are engineering challenges that we have to overcome. But oil wasn't easy to extract from the ground either. So the oil age was brought about by a lot of engineering triumphs. The renewable age, likewise, can be. And really, for our economy to survive in any form that we know it, it has to. So electrical vehicles are a part of any future because most of our most oil consumption is from or is in the transportation sector. So planes, ships, automobiles, all of those, if we can eliminate internal combustion or vastly reduce it, then we're increasing our chances of mitigating this entire crisis. And if we can then provide electricity from renewable sources, that's really where the rubber will meet the road in terms of averting the worst of this. Now, just one other look at the Paris Agreement in terms of its stated goal is to limit temperature increase to 1.5 degrees Celsius by 2050. Now, it's not that that's any magical number in terms of like a physical limit, but it's judged as being economically feasible so that it's not going to inflict too much pain to transition away from our existing energy economy to a new one and still limit the environmental impacts from global warming. So offshore wind is a component of this. It's finally come to the eastern United States. It's been in Europe for about 10 years. So we now are basically feeding off of their knowledge because they have a number of operating wind farms there that are doing quite nicely. And so global wind potential, the estimates on this vary by quite a bit. I've seen as low as 10% globally to over half of our electricity demand globally could be met by wind farms. But even if it's toward the lower end, the potential of solar, whether it's photovoltaic or otherwise, is even greater. And one nice sort of dovetail element to this is that where wind power fails, solar tends to do well. Because when you're closer to the equatorial zone where the winds aren't necessarily as strong, that's where solar is most effective. So those two alone, I think, could serve to address most of our energy needs over coming decades, but we need to act quickly because we only have probably anywhere from 3 to 5 decades to really make this transition. Otherwise, we won't be able to. So in terms of what I'm doing right now, that is the Go Pursuit. It's a service vessel that works in the Gulf. And right now the back end is loaded with a bunch of steel boxes and survey equipment. And they right now are south of Cape Cod. And so I was working southwest of Martha's Vineyard there a couple of weeks ago, and I'm going back next Tuesday for another 6-week deployment. And so these are the mapped out zones for a number of wind farms that are in development now. So the data is being gathered, the plans are being made for the farms to be built, and over the next 10 years, most of those should come into operation. And so I'm hoping to take a part in building these, and hopefully before too long, we will be able to meet at least a good portion of the East Coast energy needs with the wind off the coast there. So with that, I'd like to thank you for your time and open it up to you if anyone has any questions.
Really interesting. When we were organizing this, we realized the people.
I'll repeat it, of course.
Why don't we go back to gallery view also so that you and we can see the audience?
Okay, yes. So so I'll turn off stop sharing.
And then in the upper right hand corner, you'll see.
I see view.
The stop share should be a black.
Yeah, no, I see me, and then I see a few other.
Stop share.
It's just not.
No, I did. I think it's just my screen's bigger, but I think I'm back to, if you want to come and take a quick look.
He's good, it's just not showing on the projector.
That's it.
Yeah.
So
Oh, yeah, no, it's still,
how can we-
let me just turn off the PowerPoint. How about that?
Yeah.
And
Gene Stearns is asking.
okay, a question on how is electricity generated on the wind farm? So the wind, if you've seen, even a small turbine on land, a number of houses around here have domestic size turbines. So we've got a tower with usually the 3 blades rotating. So those blades are connected to a generator. So the body on top of the tower is called the nacelle. And then the nacelle houses a turbine, and it's driven by the blades, which are propelled by the wind. And so that turbine then is what spins and generates the electricity, exactly the way a power plant fired by coal or oil or gas would be. It's the same principle, but the fuel is wind instead of hot water, due to burning fuel. Is that where the questions are coming in? Back there? Yeah, I think she's looking after the okay.
So many of these and actually coupled with storage systems that spread out.
That's
Demand.
yes.
And a piece of the question. And then that raises a whole set of issues about the need for rare earths and other very problematic minerals. I wonder if you just talk about
There's a question about the necessity in renewable energy systems for energy storage, since the generation is very intermittent, it's very uneven. So we need to be able to spread out that energy across time, and how to accomplish that, especially since the batteries that we use tend to need the rare earth elements that are found in China and elsewhere around the world. And that's a very real issue. I come back to the well-worn phrase that there is no free lunch, that there is no perfect solution, there is no silver bullet. And so China has been a source of those, where basically they're called rare earth because they're present dispersed throughout bedrock. And so what you simply need to do is process tons and tons of bedrock to get a small amount of these elements like lithium and others that are at present critical for battery manufacture. And so Greenland is apparently another area, of course, covered by ice. And that is one of the areas of most active research, is battery technology. It's come a long way in terms of capacity, and in terms of our being able to work around rare earths, I can't say specifically. I know that is a very active topic of research for exactly the reasons you listed, that they're extremely destructive to the environment, and thinking in more strategic terms, we don't want to depend on China or places like that for our economy. It's just, in terms of energy security, we'd rather be able to find things here domestically or, with more secure allies. So eliminating rare earths from the entire equation would be the best possibility, but chemically, I can't tell you how close we are to doing that.
I have a question.
Okay, sure.
I didn't, and I don't know the right terms because everything you were saying went past me very quickly. But when you were speaking at the beginning about the historic rise ocean in the oceans from underwater volcanic activity. Is that likely to happen again? Could that
It could, but we're talking, occurrences like that take place over the course of tens of millions of years.
right?
It's not something that happens. Yeah, I'm not aware, of any sort of uptick in global volcanic activity. And again, these are things that it would take thousands of years for them to even really become apparent. So it's nothing that's going to impact us, globally, really during any number of lifetimes of humans that we know. Yeah.
There's a question in the chat from Ben Atkinson. It says, what are the most important changes we can make individual level
buy electric cars, transition to solar energy at our homes if possible?
Well, those are on the list. I would say, try to live more simply, really. Just consume less energy and consume fewer resources. You know, the old, the conservationist adage, reduce, reuse, recycle. And recycling, is sometimes abused as a vanity project. I don't think it's bad to recycle things, but really reducing and reusing are the core of any sort of conservationist mentality. And that includes your use of energy. Simply making fewer trips in your car. And, we all like to travel someplace for recreation, and not that I want to destroy the tourist economy, but really, going out for the Sunday ride like we used to when I was a kid, and I'd be bored out of my skull for 2 hours, and only if we got pizza at the end could I even tolerate it. So things like that, just in a Thoreau style of reducing the extraneous parts of your life so that you're consuming fewer resources, and developing that as an ethic in your family and among the people that you know. To live basically, I'll use the term, to live more ethically in terms of our impact on the planet. And certainly, solar panels on the house. I mean, I'd love to have those at some point, and I'd love a wind turbine next to the house. But really, the simpler solutions are better, which is just use less, live more simply. That's the best I can give you.
It's really better. More impact if we use less than if we have solar panels?
Well, I'm not saying solar panels are bad, but if you're asking me, where do you start? What's the most important? Reducing your consumption is the most important, and changing your life patterns so that you don't have to consume as much is the most important. More devices on the roof or in the yard. Yeah, I mean, we need energy, but I think in terms of priority, the easiest thing to do, the first thing you can do, is reduce your consumption. You don't need to buy anything for that. You can sit down and think it out and slowly work toward a place where you're simply not driving as much, you're not using as much electricity. I think that's the simplest way for anyone to begin. It's transmitted by a cable. That's actually what we were surveying before I came in. The export cable with the ECR, because we love acronyms, of course, but depending on the number of turbines, they will be connected by a cable to usually one central transformer underwater. So all these are subsea, and that might convert it to a high voltage line that's an armored cable buried to a substation on land, where it can then be jumped up to cables to be brought either to a city or inland. But it's a subsea cable installed below the seafloor.
Yes.
Is that it? Going to close out? I'm sorry, I missed that. How far down is it? That I can't tell you. I think there are, I mean, I can speak for pipelines that when the water is less than 200 feet deep, you have to bury it at least 5 feet below the surface. Electrical cables, I'm not sure if there's a regulation on it, but generally speaking, to keep these things, safe from impacts from like hurricanes and things like that, you probably want them 5 to 10 feet deep. Because what happens, even though hurricanes aren't as common up here as they are in the Gulf, hurricanes move the seafloor around a lot, and they'll move pipelines around a lot. And you'll see a pipeline move several hundred feet because a hurricane just pushed it over, through wave action. So to prevent that problem, yeah, you want things, I would say at least 5 feet underground when you're getting close to shore.
Oh, I'm too short to be seen by this camera. I'm going to move his camera. Oh, Michael, you've gone away. I wanted to thank you.
Oh, okay.
So I just thought we should thank Michael very much. Those of us here and those of you on screen. Really, really interesting. And he's so brave to be our guinea pig for our first speaker series, our first attempt at doing something in person and on Zoom at the same time. So, and we pulled it off. It took a little while behind the scenes before you all joined, but it happened. So thank you very much indeed, Michael.
Thank you. Thank you for having me.